Alright, we're back at it here. We're still working with series. We have, let's see, 1, 2, 3, 4 problems with series. And then we get to exponentials and some logarithms. And I know that's troublesome for students. Find the general, or can be, find the general term of the series. Now, before you can find the general term, you got to kind of figure out what type of a series is it. And I noticed here that that the numbers are getting bigger, but they're not getting bigger by the same amount. I'm not, like here I'd have to add 20 to get to 24, but if I add 20 to 24, I don't get 144. So I'm thinking, okay, if I multiply by 6, 4 times 6 is 24. If I multiply by 6, 24 times 6 is 144. If I multiply by 6, 144 times 6 is 864. This means it's geometric. And the geometric formula, a sub n is equal to a sub 1 r to the n minus 1. Where that's the first term, and that is the common ratio. Now for arithmetic, it's a little bit different. I don't know if I have an arithmetic example coming up, but the arithmetic formula is a sub n is equal to a sub 1 plus, let's see, it's n minus 1 times d, I believe it is. But this is the guy we're using because this is for geometric, that's for arithmetic. So my first term, a sub 1, is 4, and my r is 6, because I'm multiplying by 6 each time. So just right into there, a sub n is equal to 4 times 6 to the n minus 1, and that's all they want. You don't even have to find a particular term. They're not asking you to find the 20th term. So it should look like this. The 4 terms up, this is always nice when they tell me, the 4 terms of a geometric sequence are shown below. 4 blank, 100, 500, 2500, and so on. What is the missing term of the sequence? This might be the easiest one yet, because you know it's geometric and they give you a couple of consecutive terms. What would you multiply times 100 to get 500? What would you multiply times 500 to get 2500? You'd multiply by 5. So to go from 4 to the second term, I'd have to multiply by 5, and that's going to be a 20, and that's my answer. That was as nice a problem as you could hope for. The answer is 20. Now here they ask you to find the sum of a series, and again, it's always nice when they tell you geometric, and in this case, I'm adding up the first 10 terms. Now, here's the formula, and you're going to have to probably have this memorized. I don't know if he's going to give you a formula page. But I'm going to suggest that you make sure that you memorize this, that the sum of the first n terms of a geometric, let's see if I can remember, is the first one times the quantity of 1 minus r to the n, all over 1 minus r, if I'm not mistaken. Where r is the common ratio, a is the first term, and n is how many terms. And in this case, n is 10. So I'm finding the sum of the first 10 terms. Well, they didn't use a. They use t, but this is your first term, it's 4, so that goes in here. 1 minus, now they give you the ratio is 2, so that's 2 to the 10th power. And you've got to have your calculator handy, don't forget your calculator. All over 1 minus 2, now 2 to the 10th power is 1024. And that's all over negative 1. So this turns out to be 4 times negative 1023, that's this part, over negative 1. A negative over a negative is positive. So I have 4 times 1023, that'd be 4092, if I'm not mistaken. That should be your sum. Okay, that's not so bad, just some calculator work. Of course, you have to make sure that you have your formula so that you can plug it in. Now this is the formula for a geometric. To find the sum of the first n arithmetic terms of an arithmetic series, I think it is, let's see if I can remember now, it's n times the quantity a sub 1 plus a sub n all over 2, if I'm not mistaken. Another one to put to memory. Geometric, arithmetic. Alright, over here, they've given us, now I'm pretty sure my copy was so bad I couldn't tell if that was a 30 or an infinity. I'm going to assume it's an infinity, and when you're adding an infinite number of terms, if it's arithmetic, it's going to go to infinity or negative infinity. But when it's geometric, and that's what I have here, this is geometric. You say, well, how do you know it's geometric? Start plugging terms in. Plug 1 in. 1 minus 1 is 0, so this is negative 2/3 to the 0 times 12. To the 0 is 1, times 12 is 12. Then I plug a 2 in. 2 minus 1 is 1, and negative 2/3 to the first is negative 2/3 times 12 is negative 8, so I'll write minus 8. Plug a 3 in. 3 minus 1, that's 2. Negative 2/3 to the second power is 4 ninths. 4 ninths times 12. Is it from a 1? All of a sudden I was thinking maybe it was supposed to be a 3 there. Let's see if I have it. Of course, it's never in front of me when I need it. Here we go, number 19. No, I think that's a 1. Maybe it, no, that might be a 3. Son of a gun, that might be a 3 here. Alright, so let's get rid of this. I guess it depends on what the number is. It's such small print that I can't read that. I can't tell if that's a 1 or a 3. So let's assume it's a 3. So if I plug 3 in here, 3 minus 1 is 2 squared, 4 ninths. That's 4 ninths times 12. 4 ninths times 12. I think I did this already. This turns out to be 16/3. And since I have a ratio here of negative 2/3, the absolute value of my ratio is less than 1. I can use this formula to find the sum of all these terms. It is the first term all over 1 minus r. So my first term is 16/3 all over 1 minus r, which is negative 2/3. So this is 16/3 over 5/3. 16/3 times 3/5 is 16/5. Is that a choice? It is. It's answer B. I hope I have those numbers right, because yeah, I think that's supposed to be 16/5. I think that's answer B. It's too much of a coincidence, because that's got to be a 3 and that's got to be an infinity. Otherwise, if this was a 30, what a mess this would be. You'd get some really weird looking fractions. So 16/5 appears to be the right answer here. Now again, I can only use this formula here for geometric series if it's infinite and if the absolute value of the ratio is less than 1, and my ratio was negative 2/3. So the absolute value of negative 2/3 is positive 2/3, which means it's less than 1. Kind of like between 0 and 1 there, like that. All right, now, series, sequences, exponential functions, logarithmic functions. All right, what value of x makes this statement true? Oh, you can't ask for a nicer one than this. 2 to the x equals 8 is 2 to the third. See, I can match the bases. And that means if the bases are the same, the exponents are equal. There you go, first one done. I can't match the bases here though, because this is a prime number and this is a prime number. So what I'm going to do here is I am going to use the fact that I have two positive numbers here. I can take the log of both sides. And then I can use a property. There are 3 or 4 key properties of logarithms, but one of my properties allows me to change this by taking the x as the exponent and bringing it out in front of the logarithm as a factor. And now it's easy pleasy, because I'm going to divide both sides by log 5 to find out what x is. And I get x is equal to this mess. This is a base 10 logarithm. I don't remember if he wrote down 10s or not. He did write down 10s. Okay, this is a base 10 logarithm. And that would match up with the answer D there. So in this case, I have to use one of the properties of logarithms. Let's see if you can remember these. The log of m times n for any base is the log base b of m plus the log base b of n. The second one, the log base b of m divided by n is the log base b of m minus the log base b of n. And the one that I use, the log base b of, m to the k is equal to k times the log base b of m. It's like the exponent comes out in front. And of course, there are other laws of logarithms and properties of logarithms. That one's key. I'll put one more down here, that if the log base b of m equals the log base b of n, that implies that m equals n. And if m and n are positive, it works the other way around. The converse works as well. All right, problem 22. Problem 22 involves the definition of what a logarithm is based on the idea of what an exponential function is. See, the exponential functions and logarithmic functions are inverses of one another. So if I write down something like y equals, I don't know, b to the x, where b is some positive number not equal to 1, to find the inverse, you interchange the x and the y. And then you solve for y. But y will be up there. We define y as the log base b of x. Well, hang on a second. Did I get that right? Yeah, for the inverse. All right, now, what I would suggest, these are inverse functions. These are not equivalent functions. But what I would suggest is to know how to convert from this form into a logarithmic form and a logarithmic form into this form. So I'm going to write that, and I don't have much space, so I'm going to have to clear out a little bit here. This is really important because I noticed that this was used on several of the questions. That if you have b to the k is equal to m, this implies that the log base b, notice the base of the exponents, the base of the log of m is equal to k. Remember, a logarithm is the exponent. Okay? Now I always tell students to kind of think of it as like if I'm going from this form to this form, drop the log and bring the b over and then nudge the k out of the way so it kind of goes up and to the right. You need to be able to convert from this form to that form and vice versa. And that's exactly what I have to do here. See, I don't know what number that if I had 2 to the, well actually I kind of do, but what number goes here just by the main look of it because of the fact that it's a logarithm, and I'm not 100% sure of all my logarithms and such, but I can convert this form into this form by bringing the exponent, or bringing the base up and treating this value up here like it becomes the new exponent. So that leaves me x, the log gets dropped, equals 2 to the negative 3, which is 1 over 2 to the third, which is 1/8. And that's what x is equal to. Now, I have to use that here, I have to use that here, and I thought there was one more. Maybe it's after number 25. But you're going to have to do it at least twice on the practice, so you figure at least once on the test, maybe twice. And I'm going to do exactly what I did just a second ago. I'm going to bring the 2 over here, and I get x equals 10, the 10 over here, and that drives the, kind of nudges it right up, the negative 2 here. So I have 1 over 10 squared, because that's what negative 2 exponent means. So it's 1 over 100. Is that a choice? I don't even know if that's a choice there. Yes, it is. All right, I have 2 more here. Now this guy here kind of uses this guy here. I have the same base log, and they're said equal, so the log of something equals the log of something. The somethings must be equal. So I can jump right away to this. I can add 1. I can take the square root of both sides. I get plus or minus 3. Now you say, oh, be careful. Can't take the log of a negative number. Well, even if you put negative 3 in there, you're going to square it. It's going to become positive 9 minus 1, and that's going to work out. So in this case, both answers. But on these log equations, make sure that if you were to plug them back into the original problem, that you don't get a log of a negative number. All right, one more down here with an equation. I want you to find x, but this time I have 3 logarithms. There's my variable. But on right here on the right side is where I use this property, kind of in reverse. I'm going to go from here to here. I'm going to combine these so that I get the log of something equals the log of something else. I want to have a single log over here. You can always tell if it's a single log as compared, because it's happy as compared to a married log. Okay, so this is log of 4 times x. The product. This is from the sum to the product right here. So now if this equals this, that means 28 equals 4x. Divide by 4, x is 7. So if you go back and plug 7 and you can see that you have the log of a positive number, that's a good thing. There's your answer, and we are done with the first half of the multiple choice problems.